Hello. Hopefully we're all doing well. I think we still have people coming in. So we will wait a few minutes. Oh, not a few minutes, maybe 2 minutes, and then we'll get going. Thanks. All right, everyone. We still have people coming in, but I will get going. The session is being recorded, and hopefully it's useful to you. And one of the things that we covered last week was how, well, it was a crash course in deep learning and how you can actually build a deep learning model. And I kind of glossed over the model itself, but I went through what in depth on what a deep learning model looks like, how you can do your AI work, and do some tracking, or testing and analysis. We covered this morning. And now, today, we want to go over all the different types of models. Models for vision, for language processing, graphs, and other things. If you are specifically interested in graph neural networks, earlier this week on Tuesday, we had a couple of talks on graphs that covered in more depth than I will. So if you're interested in graphs specifically, look into that. But deep learning is quite a big area and a lot of models. So I just wanted to go through all of the main ones. And no matter what model you're looking at, one of the most important model of them all is something we call the autoencoder. And I briefly went over this last week, and I talked about how a neural network, two-layer neural network, can approximate any nonlinear function. But to do so, if you have the input and you have the output, and there's one layer in the middle, this layer had to be infinitely wide to achieve arbitrary precision. So it's wide, like this. Turns out, as you add layers, the network does not have to be that wide, but we get deeper. And the more layers we add, the deeper the network is. And this is where the whole thing about deep learning comes in. So by having multiple layers in your network, you can actually have a just as powerful network as you would have a wide network. And in fact, the deepness of your network kind of gives it just as much power as, a significantly wider network. So it's far more efficient to be deeper. And we'll see there's been problems where if it's too deep, you get some sort of smoothing or over smoothing. And we'll see solutions to that. And that gives rise to new types of models. But the most basic one that we want to talk about, and the most basic concept that you should understand, is this idea of an autoencoder. And an autoencoder has an encoder part and a decoder part. Now, what is it doing? You have this idea that you have an input layer like this, and you have an output layer like this. When we have an autoencoder, what we actually have is the input and the output are the same data. That's where the auto comes in. So we kind of have the same input and the same output. But what we're trying to do is we're basically saying, if we set up a scenario where the input is the output, and we pass all of that information from the input through smaller and smaller layers, eventually to this latent space, and we've discussed latent space a few times already in our events, but the latent space is sort of like a hidden space. And this latent space here is the smallest it ever gets. And so we're effectively passing the information contained in the input through what we call a bottleneck. And so all of the information needs to go through and reduce down to, in this case, just 3 neurons. But then from those 3 neurons, you need to recover the input again. And this bottleneck structure is incredibly important, because what it forces the neural network to do is to learn all the weights needed to reduce the input firstly, and then also to create various forms of this latent space that allow you to recover the input given the latent space. So that's what the encoder does. The encoder takes the input, which may have, in this case, I don't know, 10 inputs, 10 pixel values, or it's a vector of length 10, and then we reduce it down to a vector of length 3. So that's encoding the information, compressing it, and then it takes the compressed information and is able to restore it. And you'd run this through the training process, which is an optimization process. And the idea is that the input is compressed. All of your training data, which corresponds to a size of vector 10, is compressed to a latent representation of which is much smaller. So it's compressed. But then from that compressed representation, we can restore the input. And this idea of an autoencoder, of a bottleneck, you will see repeatedly throughout various models. And in fact, if you watch the recordings, or if you did attend on Friday last week about stable diffusion, we have something called a variational autoencoder that's used within that sophisticated network to try to understand basically this code here. And the bottleneck is important because you effectively create this space, and this space usually ends up being a manifold. And a manifold we talked about as a sort of a smooth curved surface you can think of, but it's taking all your data and projecting it down into this manifold, and then you can recover things from the manifold. And things like latent diffusion now, latent diffusion or stable diffusion do cool things with this code that you get to try and model those amazing images, so that you can inject things into this code to try to recover amazing images. Okay, so that's an important part. It's worth having a go if you are trying to understand this. Here's some nice links, particularly the Keras one, where they look at all the types of autoencoders. You can have things that remove noise. So you have a noisy image and a clean image, and it will remove the noise. And this idea of a bottleneck allows you to learn this representation that's important. And then lastly, the key thing about this compression is that it's a data-driven compression, right? We haven't told it about anything to do with what you're supposed to learn there. We've just said, solve this problem. Input, output, bottleneck. What is the best representation here? And in a way, it's a data-driven representation. Depending on the data, you get a specific code. And that could it itself be useful, because if you have some data, then you're not sure what are the main basis functions for it. What is a compressed representation? This neural network works it out for you. Okay, so that's really important. So the first type I wanted to talk to you about was where really the deep learning kind of took off. And it started in computer vision. And for that, we need to understand what vision is. So back in the 60s, these guys were doing experiments with a cat's vision system, and they're trying to work out what actually makes up the vision of a cat. So they looked at the cat's visual cortex and showing various shapes to the cat. So the cat is strapped down and showing things to the cat, and while measuring signals from the brain. They showed various images and they got no response at all. But as you take out, I guess, glass slides from a projector, you see the shadows of the edges of the slide as you slide them through onto the screen. And that's when the cat's eye was responding, not to the objects they were showing. And so the edges of the slides that cause the response. And it turns out that cat's eyes responds to oriented lines. So when they see oriented lines, the visual cortex is able to process it. It triggers processing. And they mapped this in their cortex in the way of which part of the cortex corresponds to which line. And so this cortex part actually corresponds to different parts of lines, or different orientations of lines. And they got the Nobel Prize for it. Later on, the work was found out that we have this concept of a receptive field. So basically, this is where they found out what objects causes the response. And here later on, they found out the functions that are responsible that pick up those lines, so they are able to analyze those lines, so they give you that response in the visual cortex. And these are things called receptive fields, and they're basically sort of like a wavy line or wavy function. It's like a derivative function where you have a sort of a bright signal in the middle and dark signal, and so it responds to different orientations. And you can see here, you can model these using some maths, and you can get something called a Gabor filter. And in this paper, they showed that most of these oriented functions, these Gabor filters, actually correspond to what they measure in monkeys. And so the visual response to lines and other aspects of the vision system all relies upon these receptive fields. And here's some more examples of the types of receptive fields that you need for different orientations. And so what do they do? Well, if you have an image like this, you use some Gabor filters, you get an image like this. And so you can see that our eyes as a mammalian vision system, it kind of accentuates all of the textures, the colors, the edges, the gradients within an image, so that we can make sense of things, especially things that are important to us. And you will see that in many cases, when you look at these, what we'll see, convolutional neural networks, we'll see that these networks actually learn these receptive fields as a data-driven exercise. So we don't tell it to learn receptive fields, we tell it to learn filters, and we just assume that whatever the filters you want to learn. And when they learn those filters, it turns out they learn the filters that correspond to receptive fields. And here's some more examples. And these are the actual filters or receptive fields learned by a model called AlexNet in the early days of 2012. And you can see these are the things that also correspond to the mammalian vision system. All right, and we'll see what this idea of a convolution is. And so before we go on to that, what is an image? Just to make sure, here is what we used to do. We did it by hand. We process neighborhoods. So here's sort of a neighborhood of pixels. You get lots of pixels here, and you can do things to it. You can, blur it. You can downsample it, and you can look at the high frequencies. And this is the area of image processing before deep learning. And so the biggest impact, the first deep learning that came about was this paper here, where they developed quite a simple network to try to classify very simple objects into their classes. In this case, you have something called ImageNet, which has, I think 1,000 different categories and 1.4 million images, and the network is designed to learn what it needed to process all of those images to classify them into the 1,000 classes. And this is called AlexNet. The details here are not that important. What is important is this sort of graph, or to tell you the amount of, to show you the amount of impact that this had. So early on, in the 2012s and 13s, before that, nearly 30 to 40 years, the best we could do in this image database was around 50%. So, half the time you were right and half the time you were wrong. For 1,000 classes, that isn't too bad, but for the most part, it's not that great. Until AlexNet and CNNs came along. And within a few years, we'd reach 75, up to 80, and now we're up to about 90%. So these things are able to learn the receptive fields needed. And this was effectively our way of solving the vision problem. Something that we thought we could do in the 1960s and thought it would be an easy problem, but it took us until the, mid 2010s to kind of sort out. So the question is, what is a convolution? It's basically a sliding window. So you have a sliding window across and you're doing effectively a dot product. So you come up with something called a kernel. So you have, in this case, 3x3 kernel, and you have some values in there. And you basically take a window of your data, for example, there, and then you multiply each pixel. So it's element-wise multiplication. And then where the dot product comes in is you take the sum of all of the individual products. And then you place the result in the result area. And that's it. And then you slide the window across and redo it again. Now, the key thing that's image convolution. The key thing in the networks is that we want to learn these kernels. So what are the individual weights here that we should use? Here we've got a preset value, but what are the individual values we're going to learn so that they end up applying across the image so that they process the image for us. And we do that with many different kernels. So we might have 60 kernels or 100 kernels. And then we do that in many layers. And that's essentially our convolutional neural network. And the way it works is you have a layer, which is the input. And in the next layer, the convolution, as you saw, is a sliding window, but basically it looks at a window, and a window is around a central pixel, the neighborhood. So we're looking at a neighborhood and we're kind of computing a filter. The best set of filters, the data-driven filters, needed to process those neighborhoods. But then at the next stage, so that's our neighborhood process. The next stage is to process the neighborhoods of neighborhoods, and then the neighborhoods of the neighborhoods of the neighborhoods, and so on, until we reach the end where we look at all of the possible neighborhoods, aggregate them together, and make a decision. Now, the decision then goes back in a process called backpropagation, goes back, and we adjust the weights so we get the right class output here. And as we adjust them, we learn the filters. And as the filters are learned, we see features emerging. So here in the beginning, because we're just looking at individual pixels, what we actually learn here is low-level features like Gabor filters, as we talked about. So we're trying to extract lines. But later on, at this stage here, we've already extracted all the lines. So a later stage, what happens is we're looking at neighborhoods of neighborhoods. We start looking at extracting all of the I guess, parts of the face, eyes, noses, and all that sort of stuff. And then later on, we're looking at the neighborhoods of neighborhoods. So now we're putting together faces. And as the faces are put together, we aggregate the correct faces for the correct output. And when you do this across different things, you do it off faces, this is what you get. Cars, you start to see, circles or wheels, and then you start looking at the silhouettes of the cars. Elephants, you start looking at trunks and ears. Chairs, you start looking at the backs, faces, and when you put them all together, they're all mixed together. And so that's the essence of what a CNN does. And just to show it to you here, here's a receptive field. Here's what it looks like in 3D, sort of. So it's got this little big bump in the middle. So in a way, it's trying to pick up anything that changes along this direction. And that's what we want to do. And you have this receptive field being applied to the image to give you like this feature map, which is going to be the result of applying the receptive field. And as we go deeper, we extract more abstract features related to the data and the objects and the patterns that we want. All right, and these CNNs, they end up mimicking our human vision system, and that's their purpose. And in a way, as I said, it's a hierarchical decomposition of the image into, first of all, low-level features, and then eventually higher and higher level features, which are then aggregated. And this aggregation or averaging allows us to then extract the features that we correspond to. And remember, neurons have activation layers or activation functions. And so after a while, depending on the different classes, different parts of filters activate depending on what the input is and what the desired output is required. Okay, so here's a sort of a more 3D representation of this idea of putting together the autoencoder with a CNN. And so here's an encoder. So an encoder would have an images input. It would have a series of, it would learn a series of kernels whose outputs would produce this layer of images here. And then then usually what we do is we reduce the size of the data. In this case, we do a downsampling. And the downsampling, we downsample the data and then work out the new set of filters on that smaller set of data or lower resolution data. And the result of which is over here, and so on. And we keep learning and learning and learning until we come up to our latent space that we talked about. A decoder is something that takes the latent space and then does the opposite operations. And it ends up giving our reconstruction. So an autoencoder would basically be these two things combined. And we'll see later, we'll have things like the UNet, which will have special things called skip connections, which we'll explain soon. And we'll also have a generative adversarial network, which actually treats these two networks as two separate networks fighting each other. And the result of which gives you very realistic images. So that's the basics of the CNN. So now let's go on to the main part, which is all the different models that we have. And the first, probably one of the most important models in any forms of data, but particularly in vision, is called the UNet. And you can see that you've got sort of like a UNet type structure, and that you see in the next slide, you'll see why it's also called more of a UNet. But basically, it's an autoencoder. So we have the encoder decoder like we did before. But the important thing now is we have these ideas of skip connections. So basically what happens here is you can do a number of things. You can take this layer, because it's the same size as this layer, you can add the information to this layer. You can do that physically by adding it, and we'll see that ends up being what's called a residual connection. Or we can concatenate this, the set of filters learned here over here. And what that means is that we transfer some information. Now remember, there's some downsampling here. So we're actually losing information deliberately so that we can encode it. But sometimes we lose too much information. And we'll see in imaging that that's a detriment to us when we're trying to do imaging. So if we didn't have this skip connections, for example, if we used images here, what will happen is that you get a nice clear image here, and you get an image that almost looks like the input, but it will be blurry. And that's because we've lost some finer details during this downsampling process that this upsampling process can't recover. However, if we do copy some information over from the downsampling step, so none of the information is lost, you see that this image and this image is reconstructed perfectly. Okay, and this is the original work that it comes from. They call it skip connections. It's called the UNet. And here you can see the UNet type structure. And the UNet is also an important thing in stable diffusion and other models. And basically you have an input image file. Here's some sizes indicated, and here we learned 64 different kernels, which gives us 64 feature maps. But then we do a downsampling operation, and in this case, what they do is a max pooling, and that's basically for a 2x2 window to choose the maximum. And the reasoning behind that is that you try to keep the important, what we think is the important information, the most bright information, which will be the highest, the maximum values. And we try to retain the maximum values with all these red arrows. And we come down, but when we do come down, because we now have a smaller image, half the size, we try to learn double the number of filters. And it gives us double the number of feature maps. And then we do that again, until we come to a latent space. And here we hope to have learned all of the information corresponding to our object. And then we begin the recovery process, which is an up convolution or a convolution transpose or an upsampling. And basically, again, we have a series of weights we try to learn that restores the image. So it goes from, so it creates an additional 2x2 window, and then we place a learned number from what we get from the previous layer. And those are all the green dots. And then we basically undo the process that we've done so far in the downsampling step to get back to our output. And in this case, we're trying to do something called a segmentation, which is basically dense classification. For every pixel, we try to classify if it belongs to one of n classes. And so here's the input and here's the output. So the output is colored by the different classes that they have in the image. Now, what happens is if you don't have these gray skip connections, what happens is that this is going to be blurry and it's not going to be very accurate and sharp. However, if you do have the skip connections, what we do is we take basically the same amount of, roughly the same amount of filters, and we join it or concat it in this unit to the filters here. It gives us a way of restoring this image to a more clearer form. And this is the unit. Now, concatenation involves basically taking filters learned and then joining it to more filters. So basically you get huge memory growth and large amount of memory usage. And the other thing that was noticed with AlexNet, that as we added layers, what happens is the number of layers as you increase, you end up doing so many operations that you begin to lose information. It's sort of like, you know, a river flowing downstream. At some point, the water is filtered so much, and if you don't increase the amount of volume of water going through, the water just reduces to a trickle. It's sort of something similar like that. The way I like to look at it is you could track each of the individual values or the absolute values as you go through a network, but it's much easier to track the differences at each layer. And this is what you're effectively doing. So to overcome these issues, what's proposed is a residual connection. And it gives us probably the most important and most powerful default network that you probably could use in imaging, or in fact use in any type of deep learning, and that's called the ResNet and residual connections. And the idea is quite a simple one. You have what you might call a skip connection. You have lots of layers, but when you enter, before you enter a layer, you save that result. You do all of the layers, and at the end, you add that result back in. What that does is it forces all of these layers in here to be the residual of that input. So what you're trying to track, your network only handles the differences here. And that means regardless of how deep the network is, each part of these layers within the residual connection always looks at the residual, the differences. And so there's no trickle down effect. There's no smoothing or loss of information. You're always just looking at differences. And that means you can have very deep networks. So ResNet, in the paper produced here, one of the most successful papers in deep learning ever, they can do 150 layers and they get an incredible result for the ImageNet, something like 85% accuracy, which is pretty good. I broke records. And this idea of connections you'll see repeatedly throughout deep learning. Whenever you have a lot of complicated hardwares, you will see a skip connection jumping over across just to make sure that no information is lost. Okay. Eventually, what really showed why skip connections work is this paper on DenseNet, where every layer is skipped. And so there's dense connections across every single layer. So for example, before this layer, you skip across every single layer. And for the green one, you have one where you just skip over the purple one and go to the yellow one. There's another one that skips over the purple and the yellow one and goes straight to the orange one, and so on. What their work showed was that, yes, you're trying to keep track of only the residual, but in fact, what's actually happening is, remember, we are solving a neural network. We have an idea of something called backpropagation, where you're using the gradient. So it's an optimization process, if you remember. So at the end, we have the result, and we change the network towards the end slightly and propagate all of those changes back through the network to make it perform a little bit better. So we move towards a lower cost, a better performing network, and therefore we propagate the changes through the rest of the network so that the weights converge to the best possible value. It turns out it's best to always, because you're doing this backpropagation, a lot of these values are being updated. It's always best to minimize the distance that the gradients has to travel to get to all of those different weights. So all this is doing is, instead of a gradient step or a small change to the weights having to go through 1, 2, 3, 4 layers to the red layer, the minimal distances is there's one, you can go to the red layer directly. So it has a very small distance it needs to travel. So you're minimizing the path length for the gradient to travel. And doing that means your network will train faster and actually achieve higher accuracies with more layers. Related to this is some other work on self-similar connections. So it may be too difficult to get into the details of this, but this work introduced the idea that you can have residual connections, but is there another way to track differences, and that is one way is to create a self-similar network, so that you have a network, and then inside that network is another network that has a very similar structure, and then inside that network has the same similar structure. And so you can see here that this is one red bar with all of this stuff. No, two of this stuff, one red bar and two of this stuff. And then here you have one red bar with two of this stuff. Right? And here you have one red bar with two of this stuff here. And the idea is that each self-similar copy is basically keeps track of a residual. And so you don't need residual connections. These fractals or the self-similar networks handle the residuals themselves, which is really cool. And then they have many of these in the line. Okay, so achieving this residual connection is quite important, and there's a few ways you can do it. Now, sometimes, especially for language processing and for sequential data, you need to iterate over your data. Or alternatively, you have a string of data that you need to process one at a time. And this is where recurrent connections come in. So we looked at residual connections, now we look at recurrent connections. And so basically, it's this idea that you have one element that goes through your network to produce the output, but the output and the next element, its result is actually dependent on the preceding result to produce the current result. So, so here the girl, the network processes the girl, but requires the result of the previous word to produce its output, and likewise walked, and so on. And this was famed to be the best way of trying to mimic the human brain, because you can structure it in such a way that you can build a short-term memory. So sometimes these are referred to as LSTMs, so long-term, short-term memory. And the recurrence of this can store memory. And you can kind of look at it similarly like this. So the result goes in and then parts of it recur. But we'll see that now that transformers are actually a more efficient implementation of these recurrent connections. So in reality, well, at this time, you probably shouldn't use LSTMs or recurrent connections in practice. You should use transformers instead, but this is a very powerful idea. The problem, of course, down here is what is it if you want to process only the word certainly? And the problem is it depends on all of the previous results. And that means you have to process all of the previous results to get to the final result. And that makes training very slow. It's a sequential network. Transformers speed this up by doing all of this in parallel. And we'll get to that briefly today, but in much more detail on Friday when we have a Transformers, the day of the Transformer. Okay, so we saw normal CNNs, but there are things called regional CNNs or region CNNs, RCNNs. And the reason for this is, in general, we don't look at an image like all of it. We really just identify regions of interest. And in our way, because all our images are square, in processing terms, we look at bounding boxes. So these are all bounding boxes, and you can identify a person, a bus, all of these things. And so, you know, you don't really, sometimes in some applications also, you don't really care who the person actually is, but we just want to identify the person in the image. And so a bounding box around a person is just as good. And so we have these things called region CNNs. And basically you start out, the way they work is that you have convolutional layers, just like a normal CNN, and then you have some sort of region network. In this case, for faster RCNNs, you have a region proposal network. So basically you take the feature maps from the CNN and you look at all of the possible bounding boxes, and you might have bounding box prescribed shapes. So maybe if you're looking for a person, it's usually rectangular like this. You might have a few different shapes, and you process all of the possible ones in the feature maps. You present some proposals, you pull them all together, and then you have a classifier that'll classify which ones are the most probable. And here's some of that running. So here's something that was, 4K footage running at about 4 frames per second. This was a couple of years ago. So we've got much better technology now. This thing could run in real time at like 60 frames per second, I'm sure now. But basically you can see that you can pick up the cars and the people walking in real time. And that's the big advantage over something like the UNet, where you're processing every single pixel. You don't really need to, you just need to process the bounding boxes. And the way it does that is similar to the previous slide, but once it has all of the region of interest or ROIs, it then basically applies not a UNet, but a simpler network to try to draw around the object to get like a segmentation. And so we've used this here at UQ to do breast cancer segmentation very successfully, a very powerful network. And like always in deep learning, someone comes up with a even more efficient approach that's even faster. I need to show this. So here you might have seen that we've got, in the previous slide, we've got a few steps. So you've got a CNN, and you've got a region proposal, and then for the math CNN, we've also got a segmentation branch and a classification branch. YOLO is a network where what it actually means, you only look once. So in one step, you go from the image to all of the possible bounding boxes. And the way it does that is it breaks it down into grids, fits the bounding boxes all at once based on these grids, and gives you the final detection. So it's a lot cleaner, a lot more faster. And you can do, you have version 5 now, which, is running. What resolution is this? It's a standard, sort of standard definition or high definition running at 24 frames a second. That's not too bad. Now the works that we've also done, and another way to do more efficient CNNs is to use something called dilated convolutions. And we won't spend too much time on this, but essentially, if you remember, we always use, we showed you 3x3 convolutions. So the red dots indicate the parameters that you need to learn. So we learn these 3x3 kernels, and we slide them across the image to compute the, so here we go, to compute the kernel, the feature maps. And we learn the kernel weights to get the feature maps we want, which then gives us our correct results. The problem with that is at every layer, we need to learn more and more of these weights. And the way we get around it, essentially, for higher layers, is we were downsampling our images. Because in reality, when we try to increase the receptive field size, this light blue area, we would need a red dot in every one of these blocks. And the way we do that is we keep 3x3, but we reduce the image. So we halve the image size. And so that's one way of increasing the receptive field size. The other way, in fact, is to use something called a dilated convolution or atrous convolution, where we spread out the kernel values and we have gaps between them. And it's sort of like subsampling a kernel or a receptive field, where we still only have 9 values, but our receptive field size is much larger. And the advantage of this is we still have the same computational complexity as if we were downsampling, but we don't actually have to downsample the image to get it. And if we even make the gaps a little wider, we get even a larger receptive field size. So we can increase the receptive fields to look at larger and larger things just by dilating the convolution. And we've used this successfully in image segmentation. Now, some of you might have mesh data. So that is, you have triangulated surfaces. So here you go, you have a 3D geometry. So you might have computer graphics geometry or from game engines or something. And they're 3D objects made up of triangles. So here's the triangle here. You can actually do CNNs on these meshes too. So this mesh CNN finds a way that it looks, it's geometry with an edge. So it looks at edges, tries to define sort of a feature around those edges, and allows you to do all the same operations as you would with a CNN. So pooling, convolution, and all of those. And the end result is that you can downsample and reduce the features represented in your data that still picks up all of the important parts. So the important part here obviously is the handles. And you can see that the handles are preserved, but most of this stuff is not that important as the handles. And you can see that stuff there as well. And so they use that to process and classify meshes and to segment parts of meshes. So useful if you're using 3D models. Now, the next type of model is one of the most important types. And we talked about these things called variational autoencoders. We've already looked at stable diffusion. And at some point, we haven't really covered generative adversarial networks. I will in the next slide. But generative models are one of the most useful ones. It's where you take your data and you create this manifold out of it. And once you have the manifold, you, instead of sampling the individual data points on that manifold, which gave you the manifold, you construct this manifold and you have connections between all the points. You can now sample from the surface directly, from the manifold directly, rather than the data points that you used to construct it. So in other words, you parameterize your data set. And in doing so, you can actually sample an infinite number of points from this surface to represent your data set. And that's generative modeling. So that means you can generate data at a whim. And here, the example that we use here is a variational autoencoder. So basically an autoencoder, and we've got some constraints in the middle where it learns some parameters of a Gaussian. So a variational autoencoder basically takes your data and distributes it on a Gaussian surface. And here's the Gaussian surface. You can actually look at it from the top down. And we're trying to look at the data set of digits from 0 to 1, handwritten digits. And what it's done, it ends up learning a surface, a Gaussian surface, where each part represents a digit. So here's a 1 and a 7. And it actually shows you how you can morph from 1 to a 7, right? And how a 7 is related to a 9. A 9 is related to an 8, and even to a 0, and how a 0 is a 6 and a 5, and so on. So it works out all of these wonderful relationships from your data, all data driven. You didn't have to do anything. All you had to do is put some constraints on the types of manifold that you're trying to learn. Get more details in that link if you want it. So that was a variational autoencoder. Another way to do it is to, as I said before, set up a encoder and a decoder in an adversarial learning context. What does that mean? We're trying to create a generative adversarial network. And the concept is actually very interesting. What we're trying to do is to learn a two-player game using some game theory. So a two-player game is you have two participants. In this case, we're going to call them the generator and the discriminator. And the discriminator, you can think of as maybe the policeman, and the generator as the counterfeiter. And the police have look at real money. They know what a real money looks like. So they look at real samples and they decide, or they look at any sample actually, but you can feed in real samples and it'll tell you whether they're real or not. Interestingly enough, the generator, the counterfeiter, it actually generates fake samples. Initially, when it's not trained, it just generates rubbish. And it'll go into the discriminator, and the discriminator will be like, yeah, false. Is this real? False. It's not real. But what we're trying to do is we're trying to make the generator fool the discriminator. And this is a network. This is usually an encoder network because the image goes in and some decision or a classification comes out. And so the discriminator never knows whether we're giving in a real or fake sample. It needs to decide that. And the generator, we make it favorable so that we set up the training so that it gets a glimpse of what the discriminator uses to tell real samples. And so what happens is we actually just provided some latent space input. Now, usually what we want to do is we want to encode the data distribution into a Gaussian distribution. So this latent space ends up just being noise. So what we do is we can have any latent space, but we usually input some noise. And the generator makes an image from that noise we've given it. And then it's passed to the discriminator to classify whether it's real or not. During the training, though, as I said, these two are connected so that the generator can learn. Eventually, the generator is good enough so that it actually can fool the discriminator. And at that point, you have encoded your data into the normal distribution. And so you have this manifold. I don't think I have an animation. Oh, yes, I do. So here's an example of these MNIST digit things. The noise goes in. That produces a fake image, and the discriminator tells you it's real or fake. And so it starts out very noisy, but in the end, it begins to morph into something that looks pretty real. There's 7s and 6s. And then you can really disconnect the discriminator. You don't need it anymore. You just have a generator which can generate images for you at a whim. It passes noise and it gives you some nice output. Now, there are problems with that because if you just have noise going in, there's no way for you to know what the manifold actually looks like. And so NVIDIA, they came up with something called the style game, where, instead of putting in the noise straight away, the Z, you pass it through a network to get a W. So the noise is transformed into some other value, and you're going to learn what all of these are. And then you pass the W into your generator. And the result is this is the real distribution of your data. This is actually the distribution that you learn. If it was a Z, it's all skewed and you don't know what it is. But then if you map it to W, you can create something that's very similar to the actual distribution. And this is a YouTube video, I think, but basically I won't play it. You can play it when you have a chance. But what they can do now is that they can control, because they've got the latent space, they can actually control each of the individual parameters and the type of conditions that they can put into the generative model, and they can produce realistic faces. So trained on many different types of celebrity, I think it's not celebrity, but general faces, they can end up generating these very realistic faces. And I think in last week I talked to you about this person does not exist. There's a website where you can run this model. Anytime you refresh the page, it gives you a random face of a person that doesn't exist, but it puts together this manifold, and it picks from the manifold to generate these faces. Oops, we won't play it there. Oh, okay. Does that link? Okay, that link I might need to check, sorry. But then there's some advances to StyleGAN. Not really that important here, but basically they've further improved it so it even looks more realistic. More advancements, and this is what's actually used in stable diffusion, something called vector quantization. So we have this encoder and we have the decoder, but now instead of learning this latent space, we're actually going to learn a code book. And a code book is just a series of vectors. And we learn these vectors to try to understand what's in the data. And the code book is really useful because it's another way of basically defining what our manifold or restricting what our manifold is going to be. And it's an incredibly useful model. And the advantage of this is, remember I mentioned the variational autoencoder doesn't have skip connections. So that when you have the input compared to the output is blurry. The GAN, on the other hand, has this realism discriminator, this policeman that's supervising the generator, so that it's going to be realistic. So you actually produce very realistic samples. In this case, this is the best of both worlds in the sense that it's still an autoencoder or variational autoencoder. And so it's much easier to train than a generative adversarial network, because there you have an adversarial term. You're basically pitching one network against another, and the training ends up being chaotic. When you have an encoder and a decoder, it's much more stable training. And having just a code book also is pretty easy to train. But because we have a code book, we can actually supervise it in such a way, train it in such a way so that it still produces a realistic output. And then finally, sorry, getting close to the end now, we come to transformers. And a transformer you can kind of think of as, the easiest way I would define it as, it's sort of like an MLP. It's got MLPs everywhere as well. So you've got a feed forward here and a feed forward there, but it's got these nice front ends to it where an input comes in, and it's usually lots of inputs like tokens. So words come in and you have some sort of definition of positioning for it. So you know when one thing comes ahead of another, but basically you've got inputs, and in between the multi-layer perceptron and the input, you have a series of attention heads. And all that does is it has an attention mask, which basically tries to map the usefulness weight, the probability of how useful it is to all the other possible tokens, one token to every other token. And you have a large attention matrix. And that attention matrix is basically the really cool thing, because it allows you to speed up training, because now you have a huge matrix and you can do matrix multiplication. With the RNN, with the recurrent neural network, the LSTM or whatever you want to call it, it was all sequential. Now you've got them all in a parallel way. You can train these things in parallel. And most importantly, because you've got inputs and you've got attention and then you've got the MLPs, this attention acts as a way of the MLP, the weights are fixed, but the attention weights change depending on input, right? So that gives you a dynamic MLP if you want to kind of think about it. And that gives it its supreme power. So it's the most general type of network we have. And it allows you to learn anything, including vision. So you can pass in patches, and what we've covered, and you can go back to our AI showcase or journal club this week. We talk about new global image tokens instead of patches for vision transformers that will learn better, in fact. And when you train transformers on an extremely large data set, you get something called a large language model. And now, if you train that in an interactions, in an interaction method with humans using reinforcement learning, you get Chat GPT. And this is some really, really amazing stuff where OpenAI set up their website where you could actually go in and register and have a go at typing in things and have a chat with this AI, and it could do amazing things. So how about a step-by-step analysis of the worst time complexity algorithm of a bubble sort algorithm from a wise talking or fast talking wise guy from the 1940s gangster movie? And yeah, it's on point, you know, and it gives you code examples in Python to explain it. You know, there's other examples where people have looked at this and compared it against Google, and Google is pretty, well, stale, not very useful. So how do you represent a differential equation in LaTeX, which is this typesetting thing? And yeah, it gives an example, but doesn't. But when you ask Chat GPT, it explains everything to you and puts code examples, which you can copy and paste, right? Or format nicely. So they say even our very own fast AI, Jeremy Howard, has seen this as one of the revolutionary tools. So back then he said, he's got a tweet, I haven't got it here, but when he saw Google, he was like, this is going to be the tool of the future. Now he's looking at Chat GPT, and he's saying that this is going to be the tool of the future. And you can see this chat system replacing search. And it can do such a great job. And the knowledge, the way that it summarizes the knowledge for you, this large language model for you, is, you know, it would take you, you know, hours to doing multiple Google searches to try to summarize this. This thing can do it, you know, within seconds. It's quite amazing. And so we haven't covered reinforcement learning. I'm hoping we'll have someone on Friday to chat about it as well, or talk about it as well. But we'll definitely be covering transformers. Okay, still going on. There is a subgenre that's also available, that's also around. Now, what I've talked to you all this time are fixed architectures. You have to define them. But what if that architecture is not suited for your task? There are things called neural architecture search. So in other words, they try lots of different architectures and they end up finding the best one for you. We're not going to go into details with them, but they exist and you should be aware of them. And so maybe that'll be the next future where we have dynamic architectures that adapt depending on our data set, as well as not just the weights and the filters and the data drivenness of the algorithms, but the architecture themselves. And we've done some work with segmentation using other things like fabric networks to do neural architecture search. So basically you have a fabric of all possible links between all possible types of states of networks, and you work out your best path through it. Quite amazing, actually. And finally, this is what we covered on Friday, probabilistic diffusion models. Also pretty amazing. If you can think about it, you have a process of adding noise, and you can model this, and then you can train a network to do the reverse. And in a way, this is doing what a generative adversarial network does, but this is all wrapped up by combining variational VQ-VAEs, vector quantized variational autoencoders, and some GAN losses. And you can and you can put in some prompts into the VQ part using a transformer. So it kind of puts all of those things we talked about together. And you can write a prompt to say, I want a dog, and then it will slowly imagine a dog for you. Pretty amazing. To show you the kind of things that are being done, this is pretty amazing. Someone on Reddit is trying to use Stable Diffusion to take selfies throughout history. So here's one with Trojan horse. It's pretty funny. There's one where he's a caveman trying to run and being run down by a mammoth. So again, it's distilling or extracting the useful information out of the distribution of 3 billion images, which is pretty amazing. This is particularly topical. I'm not sure if there's English soccer fans in the audience. My condolences to you. But here's an interesting image where, you know, the English football team in tears after losing at the World Cup. Well, first I saw the image, I was like, why are they hugging a teddy bear? But then I realized it's not actually a real image, it's a generated image. So it's pretty amazing. And yeah, and that's it from me. Those are the main architectures and deep learning models that you need to keep your eye on. There are more, of course. As I said, I am available as a meet an expert, AI expert on Fridays. If you have any questions or you want to sort of learn more about individual models, or if you're not sure which model you should use, I'll be there to sort of give you some advice. But most of these models have different architectures and different advantages and disadvantages. Yeah, we'll always keep it out for new architectures. We showed you a few already. ChatGPT is literally 3 weeks old. It's had quite a bit of a storm in its development, so something to work out, and we'll talk about that on Friday. And yeah, that's it from me. Thank you for your attention. Is there any questions that you would like me to answer? I'm not sure. Hopefully it's been useful in some ways. Not sure. No questions as yet. I'm guessing there's not many. Oh. Yes, yeah. So I will be posting the slides into Slack straight after this. Are the autoencoder weights mirror images? No, actually. So they will actually be different weights because they're kind of doing two different things. They're not quite mirror. It depends on the task. It could be a mirror depending on the task. I'll put the link for the recording as well into Slack almost right after this. Zoom takes maybe half an hour to process the video files before it's available, but I'll post it. So within a couple of hours, you'll have the recording. And there's recordings for the rest of the events as well already up. Yeah, so look, there is another type of model called a Siamese network. And in that case, the encoder-decoder weights are not mirrors, but they're shared. And those sorts of setups can occur. And why they're shared is because in Siamese networks, you kind of have two different scenarios. So two Siamese networks working together on very similar tasks to try to learn usually the metric or the distance between two things, maybe positive samples and negative samples. So yes, they can be mirrored, they can be shared, but in general, they're not set to be, unless there's a specific application. What about image processing in the last 2 weeks? Does it reflect? Both is true. So yes, I have a research interest, and so there's a bit of a bias towards image processing, and I apologize. But they're really only the two major areas that are in deep learning are computer vision, that is imaging, which is why you get the bias, and the other side is natural language processing, which is where the transformers come from. So I guess a bulk of that non-imaging side we'll cover on Friday. And in the end, you know, the two big breakthroughs are stable diffusion imaging and chat GPT, natural language processing, which we'll get to on Friday. Okay, new question. Could you please tell us about multitask learning? Okay. So multitask learning, yes. So that's when you have basically networks connected together that have multiple tasks. And the way they usually combine is you'll have network A, B, and C doing different things. And the way you connect them together traditionally is by combining the loss functions together. And you are optimizing all three or all n of them together at once. Now, sometimes you use intermediate outputs, sometimes you share weights, and that's where multitask learning is better than separate learning, because if you can share the weights, if you can, for example, share the latent spaces. So, for example, you might learn to classify an image into some class, but you end up with an encoder and you have a latent space, which then gets passed to a classifier. But that latent space is learned now to classify something. You then merge that with something else. You merge that with something else, and then you do another task. That latent space that you just learned can help. So that's multitask learning, where parts of the network are learned together and parts of it are either shared or connected. So it helps another task. Yes, absolutely. So there are, for example, people have tried to do like autoencoders, and you have a classifier branch. We do multimodal learning where we have multiple inputs and we try to do the same task. But then you can have multiple networks that try to do multiple tasks. So there's a whole area in deep learning for multitask learning. Can we reach out to you for a possible Absolutely, yep. So, you know, that's basically why we've got this Q&A session on Friday. We have the Meet an AI experts that runs conjunctly with that. Just group them together because it's separately. There weren't many people involved last time. We're bringing them together. We can sort of have discussions about various things. Hopefully I've got all the questions. Do you need to specify the number of classes for image segmentation or the? That's a very interesting question. At the moment, we do define the number of classes. I guess it's part of the learning exercise. Sometimes though, you also have anomalies. So you have an anomaly detection network, in which case you don't know the number of anomalies. But yeah, deciding on the fly, I guess that would be possible too. You'd probably think of a loss. If you can think of a loss function that can do it, it'll be pretty easy to implement. If not, then maybe you can do a neural architecture search or something else, so that you have some sort of an adaptive architecture to do it. Good questions. Thank you for the questions. Any other questions? Oh, maybe one more. Can you talk about your vision for deep learning in the future after learning to break through NL? Yes. So I think. So you saw, I think Chat GPT is the future. So we've got stable diffusion breakthrough. Yeah, there are so many breakthroughs, and I think it's to do with reinforcement learning. Now, I haven't covered much reinforcement learning, and maybe next week I'll try to get a guest to try to cover some of that on Friday as well. So in deep learning, we create models. So we create a large language model, we create a diffusion model, and then we can query it. Now, the problem with that is we create this surface, right? I was talking about this manifold, and that's fine. But the manifold is, once you've trained it, it's there, it's fixed, and you're just querying the manifold. You're not creating any new data, although you are filling in the gaps, which kind of is creating some new data, like doing a selfie in with the Trojan horse. I mean, I'm pretty sure there's no image of that ever happening before, but somehow the model's done it. But there isn't really new knowledge there. What reinforcement learning does is, for example, you can set up a this agent and set it a reward function so that it does something, it learns to do something where it gets the reward. And what ChatGPT is, and why it's so good, is it's not just because it's just deep learning. It's not deep learning. It's deep learning plus reinforcement learning. And so it's taking all of this information, but it's learned how to interact with humans. And in doing so, it's actually being able to create new information to a limited extent still. I think there's still quite a lot of limitations on the reinforcement. So Jan LeCun actually, that's his opinion as well. So it's not just my opinion. He thinks the next big thing is going to be how we do reinforcement learning or something related to reinforcement learning with these large models. So you have this model, which is the knowledge base, and you have the reinforcement learning, which kind of acts as a way to learn how to use that. Do I believe in one algorithm hypothesis? No, I don't think so. AGI will be very, very hard to get. But, you know, the amount of progress we've made in the last 3 weeks. So if you'd asked me last month, I'd say we're decades away. But with ChatGPT, it kind of changes the game a little bit. It's still a long way to go because social media, as social media does, only shows you all of the good examples. I'm sure there's plenty of cases where ChatGPT fails quite badly, but we don't see it. Look, maybe as a computer scientist, if you get a chance to have a look at Turing machines or other theories of computation, and there's, you know, a famous quote by Sir Roger Penrose. Our theory of a computer does not have anything within it to encompass intelligence. So either, well, what he says is that we need a new definition of a computer to do it. So in other words, and if you've done our course here at UQ, which is comp 2048, but you know, Turing machine, theory of a computation, you'll see that a Turing machine is so simple, there is literally no place to put the intelligence. So we have to rethink the way we build our computer. And maybe ChatGPT is the first instance of that, of this new idea of a computer. So at the moment, you know, I don't think our computers can actually have that level of intelligence. There are other considerations too, like the power drain. Our brains use 60 watts of power, and it has several orders of magnitude more number of neurons than our current models do. Our graphics cards use about 500 watts to do something that's several orders of magnitude smaller. So there's a lot of gaps to cover, and we've nearly hit the physical limit to how many transistors we can put. I mean, we're at, I think last I heard, 5 nanometer fabrication process for GPUs or CPUs. We're 1 angstrom is 0.1 nanometers, I believe. So, and 1 angstrom is 1 width of a hydrogen atom. So we are very close to a physical limit. of how well we can build these things and how power efficient they are. So what do we do after that? Yes, I'm glad you raised that. So I'm hoping one of our researchers from the School of Maths and Physics will actually give us, at this time, a crash course in quantum deep learning and quantum computation. So quantum deep learning is a thing. So hopefully we'll get an introduction next week about that. I'm looking forward to that. What do you think about quantum computation? Quantum computing we teach that also in the same course I just mentioned. The problem with that is that it's very hard to build each. Basically, each computer that we currently use has a bit, and in a quantum computer you have a qubit, and a qubit can hold much more information than a bit. But we obviously use a lot of bits in our quantum computer, megabytes of them. The best we've been able to do with a quantum computer, because it's so hard to build, and quantum computing requires superconducting material, or very low temperatures. We've been managed to do about 180 qubits, which is very much to do much. So there's a long way to go for quantum computers. Quantum deep learning, can we put all of that together to build a quantum computer that is intelligent? Maybe. But yeah, AGI I think is still quite far away. All right, that kind of, yeah, the ability that's right. So, being able to speak does not give you the intelligence. What is AGI? I guess, would we even know what an AGI, if something had an AGI level of intelligence, would we know it? Would we see it? And do we have a proper definition? This is a whole area that's so pretty exciting, that all of you who are new to this area, are quite young, so it's an exciting time for you guys, for you all to explore all of these questions and try to answer these deep things. So it's definitely exciting, and we'll see what happens. I think what we'll see is more reinforcement learning with deep learning models, and as that advances, we'll see more and more sophisticated AI, and I think we'll definitely have what we call weak AI. So AI that's designed to basically interact with us and make our lives better. And I think that's a given now. Whether we have strong AI, some things that are smart as us or smarter, I'm not so sure yet. All right. That's gone beyond the scope of this talk, but I think it's an interesting discussion anyway. Thanks for the questions. Any other questions or comments? All right. Well, thank you very much, everybody, for attending. Really appreciate it. And we'll end it there. We will look forward to seeing you on Friday. So, yeah, thank you all.